This is a Ben Eater style world's worst video card that I have been working on, and I'm demonstrating hardware scrolling. So those of you who are familiar with Ben Eater's work will recognize this board as a Ben Eater clock board, and that's feeding this chip here, which is generating the hardware scrolling. I can reset the scrolling with this button here. Let it go, off it goes. The video has a little bit of lag because I'm feeding it through a very cheap USB VGA capture card, which is supposed to be able to do 30 frames per second, but clearly is unable to do anything like that. This reset button allows me to reset it back to 0. Then I let it go and it will start scrolling, and it scrolls 1 pixel for each time the clock pulses. So I had at least one user that was interested in how this works, so I want to explain that now. So first of all, this video board isn't going to look anything like a world's worst video card, but it is based directly on those principles. Let me go over its operation really quick. First of all, instead of the 10 megahertz clock chip, I'm just using a 10 megahertz crystal, and with a pair of 1 kilo ohm resistors hooked up to a couple of NOT gates that are hooked up back to back through this jumper here that you maybe can't see, but there's a jumper there connecting the output of the first one to the input of the second one. And this gives me my 10 megahertz clock signal. If you've been watching my videos, you know that's usually how I do it, because I'm too cheap to buy a $5 clock chip. These counters are a little different. Before I was using the 4040, the 744040 Cascade counters, but I didn't think that those are going to be suitable for this particular task, because I am, instead of all of the standard decode logic that was done with 8 input AND gates and a bunch of NOT gates, instead I'm doing all the logic with this flash RAM. So this is an SST 39ST010A-70. And so that is a 70 nanosecond NAND chip. So that can take up to 70 nanoseconds from when the hardware, when the address lines are settle in to when the output occurs. That's more than half the clock cycle. And if you remember the work that we did with the 744040 chips, they could take up to 64 nanoseconds to resolve all of the counters. So that would be more than a clock cycle. So I decided instead to go with these synchronous counters. These again, though, are not 161 counters. I am using an 8-bit counter so that I can have one fewer chips, and it has some interesting features. So here's the counter chip. See, it has 8 outputs, so it's an 8-bit counter. It has an output enable low, so to enable output, you have to set that, tie that to ground or set it low. It has an R clock. That is the register clock. So this chip, in addition to having a counter, the output of the counter is goes through a separate register, and the output from the counter is clocked into the register by a positive edge trigger on our clock. It also has counter clock enable, so when this is low, then the clock is enabled, and when it's high, it's not enabled. And that's used along with RCO, which is the for connecting two of these together to get up to 16 bits if 2 are together, and you can cascade more. So you can see that it says here, expansion is easily accomplished for 2 stages by connecting RCO, the first stage, to CC-CAN, that is the counter clock enable of the second stage, and then it tells you how to cascade larger stages, but we won't need that. So 2 will be plenty for us. And so then there's also the counter clock. So the pin 11, when you clock that, it inputs the counter, but that doesn't necessarily change the output if you until our clock the output will stay the same until our clock is clocked, and then whatever is in the counter will be sent out to the the output. So that has useful properties for what we're going to do here. So let me show you my circuit, and maybe you zoom in a little bit. So these are the two counter chips, and I have the clock running from my clock circuit to pin 11, the counter clock, and you can see that I have that tied to the register clock through this short jumper, and I also have that clock tied to the register clock and the clock of the next counter chip, and I have tied together RCO. It's hard to see, but it's under there. RCO is tied over here to the counter clock enable pin, as was indicated in the instructions. And then you can also see that I have tied together the counter clear. I have those tied together by this blue line, those then are going to be, that's how you can how we'll clear the counter, is using counter clear. And both of these will clear together. Now, one of the things it says in the sheet, and it makes sense if you think about it, is that if you tie C clock and R clock together, then the counter clock, the output will always be one clock pulse behind the input clock. That doesn't prove to be much of an issue for this circuit, but that's an interesting thing to note, that the internal counter, because I have these tied together, the internal counter will always be one count behind the actual counter inside the chip. Now those output lines are fed through these greenish blue wires into the lower bits of this chip, and as you'll see, I'm not using the lowest order bit, which means I'm ignoring that low order bit, and so we really have 100 because we have 100 pixels instead of 200. Our clock here is going to count to 100 for the display interval, and then for the blank interval, it's going to count the remaining 132. And so I've got the 7 highest bits of this counter, and then the 1 lowest bit. You can't really see it in there, but this wire here connects to the lowest order counter of this chip to allow us to get to 132. And those are fed into the 8 address 0 through address 7 along this flash RAM chip. And this flash RAM chip works very much like the EEPROMs that Ben Eater uses, but those are very hard to get now. It is 4 times bigger, and therefore it has extra pins. Those pins are all near the end of the chip. The write enable and the VDD, or the power input, are simply like pushed this direction 2 pins to make room for the extra pins. And so this is how basically all chips are designed, so that they all kind of match, and you can swap them pin for pin. But you do have to remember, if the size changes, you got to move the write enable pin and the power pin to the left here in the way mine is mounted. So that gives you all the low order or horizontal counts for this chip. And then the vertical are in 2 counters up here, and these are wired pretty much the same. Let me get the VGA off here. There. So you can see that better. These are also 74HC590 chips, and they're wired very similarly. You can see that we do make use, of course, of the lowest order output. We do need that. For this one, I'm skipping actually the third to highest and second to highest order counters, because we don't need those for the addresses. In other words, if you recall, when Ben was describing how he could ignore the second most significant and third most significant bits when computing the vertical blank interval in the vertical sync signal. We can do the same trick here, and I'm simply not tying this highest order bit of the low order chip to any address lines. And likewise, I'm not tying the next highest order, let's see. Yeah, I'm not tying the next highest order as well. The only one that's tied to here is this one here, which is the second, which is bit 1, A1, and this is A0. This is A1 is tied to the highest order bit of this chip. Now, this chip is capable of holding 128 kilobytes, but I'm only using 64 kilobytes of it. So this pin here, which is the highest order address line, is tied to 0 to hold this pin to use the lowest 64K of it. And so we're using 8 bits of lower or the row select, and the column also the column select uses 8 bits, and each row that is vertical is also using 8 bits. So we have a total of 16 bits or 64K memory addresses. So let's take a look at how we're gonna handle that. It's quite simple. I wanted to have a lot of signal out of this, which is to say, I wanted to be able to have any other circuitry that's going to attach to this to know very clearly what's going on. So I have defined all of these as my output. So lowest order bit 0 is going to be the horizontal sync, and that is active when low. So this will normally be 1. In the horizontal sync, it'll be 0. Vertical sync is also active low, and that's the next bit. The next one is the horizontal blank interval. So this one will be high, or 1, whenever we're in the horizontal blank interval. And the next bit is the vertical blank interval. So this will be high when we're in the vertical blank interval. This signal 4, this is the horizontal counter reset. So this signal will signal when to reset the counter. Now, if we look again at our data sheet, you'll note that the reset clear clock, that's negative going. So this will be this would normally be a negative signal. So that one also here will be that's active negative. So this will be a 1 normally, and then 0 when it's time to signal. Same thing. This is the vertical counter reset. So that will reset the vertical counter, and that will be a 1 normally. It'll go 0 when it's time to reset the vertical counter. Then this is the blank interval. So this is any blank interval, whether it's vertical or horizontal, and that will go high or 1 during the blank interval, and the display interval is the final bit, and so that will be a 1 when we're in the display and a 0 when we're in the blank interval. The blank interval will be a 1 when we're in the blank interval, and a 0 when we're in the display interval. So here I've defined all the control bits with the names that you see up there. And here I have some inverted. So I XOR with 255, which reverses all the bits. And so this is the horizontal sync inverted, the vertical sync inverted, the horizontal counter reset, and the vertical counter reset inverse. So these are horizontal sync inverse, vertical sync inverse, horizontal counter reset inverse, and vertical counter reset inverse. Now, the horizontal points of interest, after we're ignoring the 2's bit, yeah, we can skip the 2's bit, and so we are looking at well, that's not true. I should say the 1's bit. So we're ignoring bit 0. So when we ignore the 1's bit, that is the lowest order bit, then we count. We have 100 pixels, so that is the start of the horizontal blank interval. Then 105 is the start of the horizontal sync interval, and 121 is the end of the horizontal sync interval, and 132 is the end of the horizontal blank interval. And you can see that if you look at this sheet that Ben Eater's he laid this out where in clock cycles, the 200, 10, 32, and 22, if you put that in Ben-Eater pixels, which is what we're using because we're ignoring the lowest order bit, then we have 100 pixels. So that's at 100. This is at 5. This is at 16. This is at 11. And that's simply taking the actual counts here, and you basically divide by 8. And that gives you these numbers. And fortunately, it works out to integer values. And then this is the cumulative. So that's 100 plus 5 is 105. 105 plus 16 is 121. And 121 plus 11 is 132. So that is where these horizontal numbers come from. And then we have vertical lines of interest. So we have line 216. Let's take a look at that. That one's a little more hard. That's a little harder to figure out. But if you're looking at line 600, and ignore this line here, you can't ignore those. You got to keep those. But if you don't ignore these 2 bits, as we know we can do, and the reason we can ignore these bits is because these bits, when we get to this, these bits never get higher. When we get a 1 here, these bits never go above 0 in any of these. And that's why we can just ignore them. Because if we weren't ignoring them, we'd never reach them anyway. We would never reach the number 1, 1, or 1, 0, 1, 1, 0, 1, 1, 0, 0, 0. Why? Because we're going to reset when we get down to 1, 0, 0, 1. This I tried ignoring, but I realized that you can't ignore that, and you can go ahead and try that, and you'll find out that it does not work very well. You don't get a clean signal. It'll go up and down. Why? Because you'll start here with your horizontal blank interval at 601, and then eventually you'll get to that. Then and then you're going to get to the next number and 602, and that'll be fine. But when you get to 603, so 602 won't match, and then 603 will match, and so it goes off and on. So you can't ignore this one. So if we work that all out, if we work out what these numbers are in binary without these, I've just written that over here. So this turns out to be 108. This number turns out to be 109. This number is 111. This number is 122. And so those are the values that you see here, except they aren't. Oh, those were the values when I was ignoring this bit. You got to not ignore those bits. And I guess I don't have those on here. But these are the values when you don't ignore that that second lowest order bit, and you take it. Then you need 216, 217, 221, and 244. Next, I defined a function that just sets the horizontal bit. So you pass in a byte, and you pass in an x, and it checks if, first of all, it checks if we're before the horizontal blank interval start, then we just don't do anything. If we're in the front porch, that's what this is. So if we're less than this, if x is less than or equal to horizontal sync start, so we're in the front porch, then we set the byte, whatever byte we passed in, we OR it with a blanking interval, because now we're in the blank interval bit, because we're in the blank interval, and the horizontal blank interval bit, because we're in the horizontal blank interval. If we're in the horizontal sync region, then we're in the blank interval, and we're in the horizontal blank interval, so we OR with those. But we also, because it's inverted, we AND it with the horizontal sync inverse. So that was up here, horizontal sync inverse. And so that's going to be the inverse of these horizontal sync bits. So that's going to have, let's see, horizontal sync. So that's going to be all ones and then a 0. That's what this is going to be. This is going to be 1, 1, 1, 1. So 7 ones and a 0. That's what this value is going to be. So when we AND with that value, that's going to turn off that horizontal sync bit and leave all the rest unchanged. And then if we're below so if we're in the back porch, we're below the horizontal blank interval end, then we just go back to saying we're in the blanking interval and we're in the horizontal blanking interval. Else, that is say, oh, we went off the end, right? Then we need to reset the horizontal counter. In the case of a system power-up at address in between the scan lines, we also want to reset the horizontal counter to get things started. So when you first turn on the circuit, there's no guarantee the counter is going to be within our 0 to 132 that we're expecting. It could be outside that. So we want to make sure that the horizontal counter reset resets if we say we turned it on and it was at 157. We want that to reset. We don't want that to start counting. So this will set the horizontal counter reset interval for all the bytes at the end of the line, past the end of the line. We'll never get there normally, but when we first power on, we could get to those bytes. Okay, so what I do here is the usual that I do. If dunder name equals dunder main, then I call this main and I pass it this name sync prom bin, which is the name of our output file is going to be. So I open that file here and I open it as a binary file. And then in the range from Y, so scan lines Y, 0 to 256. Now remember, we're only going to 244, but we're going to want to put some data at the end, the same way we wanted to put data at the end, past the end of our normal horizontal blanking area. We're going to want to put data that forces counter resets off the end of our vertical as well, in case the counter starts up in that range. So we cycle through all 8 bits. So now if we do that, go in range 256, that'll count 0 to 255. And then we do the range 0 to 256 for X. That's going to count, again, 0 to 255. And then, and the reason we're doing that is, we have all 8 bits. So we have to clear out towards the end there. So sync and reset signals are inverted by default. So first I set up my byte to be horizontal sync or vertical sync or horizontal reset. So I should add that too. And then the horizontal and vertical counter reset. So set by So there's so there I'm setting the horizontal sync, the vertical sync, the horizontal counter reset, and the vertical counter reset. Those are all going to be set to ones. And then we check the vertical display interval. So if Y is less than the vertical blank interval start, then we're in the vertical display interval. And if X is in the horizontal is not in the horizontal blanking interval, then it's in the display interval. So then we set the byte display interval. That's the overall display interval. It's going to be set regardless of which we're in. And then we set the horizontal bits. And so we call that function that I showed earlier, and that sets the horizontal bits for the byte. Then if we're in the front porch, we do, so if we're below the beginning of the vertical sync signal, then we also want the blank interval and the vertical blank interval to be set. And then we set the horizontal bits again. If we're in the range between, if we're in the sync interval, then we want the blank interval to be set and the vertical blank interval to be set. And we also want the vertical sync inverse to be set. And it's the same trick here. We're ANDing our byte with all ones except where the vertical sync interval. So that's the second to lowest order bit. So that'll be 11111101. And so this will turn that byte off. And then we set the horizontal bits. If we're in the vertical back porch, same thing. Now we don't want to reset the vertical sync signal, but we do want to set the blank interval and the vertical blank interval. If we're not in any of those, then as this says, we just need one vertical reset normally, but because the system could start at power up with any random address, best to reset horizontal counter reset and vertical counter reset until the end of the address space. So here we are doing that with the same thing. We AND with the inverted bits. And then we write, when we're done, we write a bytes array with that byte into it. And that writes a single byte. And that's it. That's all there is to it. The hard part was kind of thinking through the logic, but it's a very simple program once you're done. So that's what's on this chip. Now, the thing about this chip is it's going to display somewhat, the outputs are going to be erratic. And that is because when this thing is changing addresses, it could put just about anything on the output. You cannot rely on the data bits while the addresses are changing. Vertical sync could be triggered, horizontal sync could be triggered, all the bits get messed up. So here we are using a D flip-flop, an 8-bit D flip-flop. Let me find the sheet for that. Here's the sheet for that. Here's the outputs of that. So basically, you've got data inputs, data are inputs, and Q are outputs. So you have D0 and D1 on pins 3 and 4. You have D2 and D3 on pins 7 and 8. You have D4 and D5 on pins 13 and 14, and D6 and D7 on pins 17, 18, and then surrounding those little 2-bit blocks of input are the outputs. So Q0, Q1, Q2, Q3, Q4, Q5. It doesn't really matter what order they are. You just have to know which bits go together. I'm not actually going to be using these in order, as you'll see in a second. But that's what's important. And then the important thing is data is put onto the data lines, but it's ignored until the clock pulses. When the clock goes from a negative to positive transition, then it pumps the data from the input to the output. There's also a reset, which can be used to set everything to zeros, and of course, power and ground. So let me get this out of the way a minute, and I'll show you what I've got going on here. So here I've got this here is D0, D1, and D2, and those will go over to what you can see is actually D2, D1, and D3, D2, and D1. And D0 is the highest order bit here. So what that means is that this is going to be, if you recall, this is the horizontal sync. So that's going to be, output of that's going to be on this pin here. This is the vertical sync. Output is going to be on this pin here, or these pins up here. The next one is the oh, I can't even remember. Let's take a look at the code. Next bit is the horizontal blank interval. So the horizontal blank interval is going to be on this pin here and here, and then the vertical blank interval is going to be this pin up here, and you can see it's attached to something. We'll see that in a minute. And then after the vertical blank interval, then you're going to get the horizontal counter reset and the vertical counter reset. And then finally, and then you've got the blank interval and then display interval. I think that's right. Yeah, blank interval and then display interval. And the way I wired it, the display interval is down here, is actually on output will be on Q0, and the blank interval will be way up here at Q7. But like I said, the order that you set them up doesn't really matter. You just have to keep track of what's where. So one thing you'll note then is that when we get to the horizontal counter reset, this purple wire runs back here and gets to the reset pin on the counter. And that's tied by this blue wire to the reset pin on this counter. And so these are reset when we reach the horizontal end of the horizontal blank interval and we hit the horizontal counter reset. And remember, that's normally 1, and then it's going to go to 0, which is going to do the reset. If we look up here, we can see that this counters 2. They're also connected by this blue wire. The reset pins are, and that pin those are reset through this gray wire, which you can see here. This gray wire is connected here. So that's connected to the vertical counter reset, and that runs up through here. It's a little hard to see because it's kind of buried under there, but that connects to right here, which is the reset pin for these counters. So that resets these counters at the appropriate counter reset time. Now, one thing is a little different. You'll notice here the clocks are, I've got the R clock, the register clock, and the C clock, the counter clock, are tied together. You don't want to do that up here. The reason is because you don't just want to clock this at the time that clocks, because remember that it's always one behind. So that doesn't matter so much here where things are at 10 megahertz, but here you don't want to be a whole scan line behind. So what we do here is you'll notice that the clock for this flip-flop this is the clock pin, and it's connected to our 10 megahertz clock. And it's also then collected here, which means every time the 10 megahertz clock goes from positive to negative, from negative to positive, then at that time, both these are going to set. So this is going to be repeatedly a whole scan line. This is going to be setting with the same value, but that doesn't matter because it won't have clocked. So it just sets the same value again. But then when the time does come, it will very quickly that we want to do a vertical reset. We don't have to wait for a separate vertical reset clock, which is never going to come because we won't ever count there if we haven't clocked the new line on here. So this will make sure that this always stays up, that those counters always stay up to date. Their registers stay up to date. Now, that is the basic operation. That's how the logic is done for the horizontal and vertical reset. You'll also notice that this pin here, this is the output enable of this chip. This chip is going to store the image. So this is just like the ROM chip in Ben Eaters. It's going to store the image, and you'll notice that its output enable is tied to this pin here, which is driven by this pin, which is the blank interval pin, which means that this pin is only, that's the blank interval pin. But this pin, so this pin goes high during the blank interval and low during the display interval. And the output enable, of course, is a negative going signal. So when the blank interval is high, then the display interval is low, and that actually when the display interval is high, then the blank interval is low, and that's what we want to turn on this. So this chip will be turned on during the display interval and turned off during the blank interval, but it's actually driven off the blank interval output because those are positive outputs, and this is active low input. So this chip just stores the image, which, of course, you've seen many times on my videos and Ben's. And these are the standard resistor arrays. I did this a little different in that this is a 15K and then the 680K, 15K, 680K, 15K, 680K, and they're tied together. So this is all the blue, all the green, all the red right next to each other. But electrically, that makes no difference at all. Now, this is where things get kind of cool here. So these counter lines, of course, go here. We also need to run the counters to the inputs on this chip in order to have the output. So here I run all the address lines. These are all the vertical address lines are running to the various upper addresses on this flash RAM. But the lower addresses, you'll notice that I'm running. These lower addresses, which are in green here, are actually running up to these other two chips. And then from these two chips, these 7, I'm not running, you notice I'm not running the lowest order, and I'm not running the highest order. So I'm only running 7 lines here. So that's 128. That can count to 128. And those lines are running to these chips. And then from these chips, those lines are run to the addresses. And then we have these other wires coming in from here. So what's that all about? Well, first of all, I can tell you that this is another HC74 590 8-bit counter. And it does exactly like these. It has It has a latch. It has a arc clock with an arc clock, and that's what this orange wire is connected to. It has a separate clock wire which is connected to a Ben Eater clock module. It has a reset pin as being held high by this 4.7 kilo ohm resistor, and then this button allows me to reset it to 0. And its outputs 1 through 7, or Q0 through Q7, or Q6 actually. Q7 is not attached to anything, but Q0 through Q6, its outputs are also attached to these chips, these mysterious chips. And so let's figure out what's going on with those chips. Oh, and this by the way, this counter, we only want this counter to be able to clock what's in it during the blanking interval. So we want this to clock sometime during the blank interval, so that this does not update in the middle of the display interval, and we'll see why that is in a minute. So we're going to connect this. What I've been doing is connecting it to the vertical sync. And that the vertical sync then will allow that to clock a new value again. It will clock it in at the time of the vertical sync, when the vertical sync actually goes high. So when we're just coming out of vertical sync and we're just starting the back porch, that's when this number will change. We'll grab the counter, whatever it is, and put it into the register on this counter chip with register. All right. So that is basically the operation of this board, except for these two mysterious chips. And I won't keep you in suspense any longer. Those are simple adder chips. Here we go. Those are 74 HCT 283 adder chips. And so you can see that it has 4 adders, A1, B1 add to S1, A0, B0 to add to S0, and so forth. So it's got 4 of those, and I've got 2 of those chips. And you can see that this also has, this is the carry bit. So it has a carry bit in, and it has a carry bit out. And so if we look at this, this is the low order bit, and you see that I have the carry in set to 0, and the carry out goes from this blue wire here over to the carry in of the next one. And so that's how you put 2 of these together. And this will add, when this does an add operation, it'll carry any output from this into this chip. Now you'll also notice that the highest order B3 on this, I have that set to 0. So the input and output of this are always going to be the same because, this is always going to add 0 to its highest order, to the 256 place, or the 128 place, if you will, which means that this can only ever add 127 to whatever the maximum value it can add to whatever value is after that. It'll rotate over back to 0. So that's what will happen here. So this adder chip, what I'm doing is I take these address lines and I put them in order here, to 0, 1, 2, 3, bits 4, 5, 6, and 7. And those get added up to with the whatever's in the output register of this counter. And when that adds it up, if it's got a 1, it'll shift everything 1 pixel to the right. If it's a 2, it'll shift everything 2 pixels to the right, and so forth. And when it gets all the way over to 127, it'll have shifted everything 127 pixels to the right, which means you're going to want to have video display in the blank interval part of your image. So you have 100, you have basically 28 bytes to the left of your image that allow you to draw some more image while this is scrolling. If you had it hooked to a computer, of course, we're just hooked to this flash RAM chip. So if you watched my last video, you know that I had written the I'd written my image creation software to allow you to input a width and a height. And this is the reason for being able to input the width is that if you're not doing a true Ben Eater, but your VGA card, but you're doing one like this, you want to have some imagery off to the edge to be able to scroll it. So that allows me to add extra width and make the image 128 pixels wide so that it would work for this. So that's how this works, and it's working pretty well. It's not quite as pretty. Let me hook the signal back up. Not quite as pretty on this video card as it is on an actual VGA monitor. Green. Horizontal sync, you'll remember, was this there, and vertical sync. Get this wire untangled. Vertical sync went to the same place as this wire that controls the register clock on that counter. And then we need ground and put in the power. And there's our bird. And if I start stepping counter, there's just like I had at the beginning. And there we go. And you can make this go as fast as you want, but unfortunately, that capture card makes it look like it's not going smoothly. But if you see that on a real VGA monitor, you'd see it's very smooth. So that's it. That's how I did that. If you have any questions, be sure to put them in the comments below. I'd be happy to answer any questions. The next thing I want to do is to add this to a Ben Eater 6502 computer. So I've been working on that. Let me give you a preview there. So this is my Ben Eater 6502 computer, and I have laid it out a little different. I put the ROM chip over here, and of course it's a flash RAM because it's hard to get those ROM chips. And I put it in a 40-pin zero in-force socket because I figure I'm going to be reprogramming this a lot. So I want that in a ZIF socket. I moved the NAND gates, address decoder NAND gates, from down here up to in here because I had a little space in here and it wasn't enough for another chip, another big chip like a RAM chip. I moved the RAM chip down here, and I moved the I/O chip, the 6522 I/O chip over just a little bit to make room for it. And then to do that, I had to actually move the LCD display off the end of it. There are some advantages to doing it this way. I can tell you that if I take my power video card, here, I can show you that because this chip is not a flash RAM, it's not an EEPROM, it's a flash RAM. It's twice as fast as an EEPROM, and I have been able to run this. This computer at the full 10 megahertz. So let me give you a preview of that. Here I'm just hooking up power to the so I'm not going to use I don't have the VGA card hooked up to my Ben Eater card yet, obviously, but I do have the clock hooked up. So I just want to run the clock signal from up there. So that's set there. So now I am running this computer at 10 megahertz. And you can see it's working. That's all I got so far is the hello world. But the fact that that works at 10 megahertz, I'm very happy with. I do not believe you'd be able to run at 10 megahertz if you're using an EEPROM. I think 5 megahertz might be about as fast as you can go, maybe slightly faster. Next thing I'm going to do is I'm going to be connecting the VGA card to the video card the same as Ben Eater does, but I'm going to have my adder boards. And there's two ways you could connect it. You could connect, I could just pipe in, so I could just take the clock chip for this, and I could connect the clock to the I/O chip. So I could connect it to one of the outputs on the I/O chip, like so. And I could do the same with the clear that I currently have on this button. I could connect that so you can clear it. And then you could clock this in, and you could easily just make it scroll by clocking it. But I think I'm not going to do that. I think what I want to do is wire in a register, a flip-flop. I'll use an 8-way D flip-flop chip like this, and a transceiver chip. And then what you'll be able to do, what I'll do is wire that up to an address so that you can actually put whatever value you want in. So you can jump around, you can go forward, you can go backwards. For this to work, if we wanted to scroll from left to right, you would have to scroll. You would have to pipe in 127 clocks to go backwards, and you'd have to do that each time. And that's going to be quite a bit slower than if we could just write to an address. So I think I'll do that. I think I'll be setting this up, getting rid of this counter, and I'll be replacing it with a register when I attach it. If you like what I'm doing, please subscribe and like the video. And I hope that you have a very good day, and I will talk to you again very soon.